Hey everyone, welcome back. Today we're tackling a Leetcode problem called partition array, such that maximum difference is k. It sounds a little complex, but don't worry. We're going to break it down together, step by step, and find a really elegant solution. Alright, so here's the task. We're given a list of numbers, which the problem calls nums, and a single number k. Our job is to split all the numbers from the list into one or more groups. The key rule is that for any group we create, the difference between the biggest number and the smallest number in that group must be less than or equal to k fruit. The goal? Find the absolute minimum number of groups we need to create to satisfy this rule for all the numbers. Let's look at this example. We have a list of numbers, 3, 6, 1, 2, and 5. And our special number k is 2. The problem shows one possible answer is to make two groups. The first group has 3, 1, and 2. The biggest number here is 3, and the smallest is 1. The difference is 2, which is exactly our allowed limit, k. So, that group is valid. The second group has 6 and 5. The difference is 6 minus 5, which is 1. That's also less than or equal to 2. So that's valid too. Since we've used all the numbers and both groups are valid, we've found a way to do it in two groups. The challenge is to prove that we can't do it with just one group. And we can't, because the max of the whole list is 6, the min is 1, and their difference is 5, which is way bigger than our k of 2. So 2 is the best we can do. So how would we approach this? My first instinct might be to try, well, every single possible combination of groups. But that would be a complete nightmare. The number of ways to partition a set grows incredibly fast. There must be a better way. Let's think about the core rule. The difference between the maximum and minimum value. Notice something important. The order of the numbers inside a group doesn't change the max or the min. A group with 1, 3, and 2 has the same max and min as a group with 3, 1, and 2. This is a huge hint. If the order inside the groups doesn't matter, maybe we can reorder the entire original list to help us find the groups more easily. And that's the key insight. Let's sort the array first. If we take our example list and sort it, we get 1, 2, 3, 5, 6. Why does this help so much? Because now, numbers that are close in value are physically next to each other in the list. This makes it much easier to group them. We can just scan through the sorted list and bundle up consecutive numbers that fit our condition. This leads us to a simple and powerful greedy strategy. First, we sort the array. Then, we start our first group with the very first number. We'll need a counter, let's set it to 1. Now, we just walk through the rest of the sorted list. For each number we see, we ask a simple question. Can this number join our current group? The check is easy. Is this new number minus the first number in our current group less than or equal to cars? If it is, great. We just add it to the group and move on. If it's not, that number is too big. It breaks the rule. We have no choice but to close our current group and start a brand new one with this number. And of course we increment our group counter. We just repeat this until we've processed every number. Let's trace this with our sorted example. The list is 1, 2, 3, 5, 6, and k is 2. First we start a new group. Our count is 1. The first number, and therefore the minimum of this group, is 1. Now we look at the next number, which is 2. Is 2 minus 1 less than or equal to 2? Yes, it is. So 2 joins the group. Next up is 3. Is 3 minus our group's starting value, 1, less than or equal to 2? Yes, it is. 3 joins the group. Then we get to 5. Is 5 minus 1 less than or equal to 2? No. Then we get to 4. 5 minus 1 is 4, which is bigger than 2. This breaks the rule. So, we must stop here. We start a brand new group. Our count goes up to 2. This new group starts with the number 5. Finally, we look at the last number, 6. Is 6 minus our new group starting value, 5, less than or equal to 2? Yes, it's just 1. So 6 joins the second group. We've reached the end of the list. Our final count is 2. It's simple, elegant, and it gives us the right answer. Alright, here is the complete Python code that implements our greedy strategy. I know it might seem like a lot at first glance, but it's actually doing exactly what we just discussed. Let's break it down into smaller, more manageable pieces. Okay, first things first. The very first line of our function simply sorts the list of numbers. This is the crucial step that makes our greedy approach possible. Next, we create a variable to hold our answer, let's call it answers, and we set it to 1. We do this because if the list has any numbers at all, we're guaranteed to need at least one group. Then, we create another variable, startVal, to keep track of the first, and therefore smallest, number in the group we're currently building. We initialize it with the very first number from our newly sorted list. Now for the heart of the solution, the loop. We iterate through the list of numbers, starting from the second element, since we've already used the first one to begin our first group. Inside the loop, we have a simple check. We take the current number we're looking at, and subtract the startVal of our current group from it. If that difference is greater than k's, it means this number cannot join our current group. When that happens, we do two things. First, we increment our answer, ans, because we're forced to create a new group. Second, we update our startVal to be this current number, because it's now the first and smallest element of our new group. And that's it. The loop continues until all numbers have been checked. So how efficient is this solution? Let's talk complexity. The most time-consuming part of our algorithm is the initial sort. Sorting a list of n items typically takes n log n time. After that, our loop just goes through the list once, which is order n time. So the overall time complexity is dominated by the sort, making it big O of n log n. This is very fast and efficient. For space, the memory we use depends on the sorting algorithm. Python's timsort can use extra space, up to order n in the worst case, but often much less. Outside of the sort, our own code only uses a couple of variables, which is constant space. So to wrap things up, what are the big ideas here? First, when you have a problem that seems to involve complex combinations, always ask yourself if sorting the input could simplify things. Here, it was the absolute key. Second, this is a great example of a greedy algorithm. By always making the choice that seems best at the moment, that is, by trying to fit as many numbers as possible into the current group, we ended up with the correct overall answer. The core logic was simple. Start a group, grow it as much as you can, and only start a new one when you're absolutely forced to. And that's it for this problem. I really hope this breakdown helped make the solution clear. If it did, a thumbs up on the video is always appreciated. Consider subscribing for more Leetcode explanations, and feel free to drop any questions in the comments below. And hey, if you're feeling extra generous, you can always support the channel through the Boba Fund. Thanks for watching, keep up the great work, and I'll see you in the next one.